Welcome everyone. We want to continue taking a look at Polyhedra for this video, and we want to take a look at scale factor, area factor, and volume factor, right? We took a look at scale factor and area factor previously, but now that we're working in 3 dimensions, right, in space, we not only have the scale factor and the area factor, but also the volume factor. So we want to take a look at that. All right. We'll begin by computing some easy surface areas and volumes, and from that we will try to make a conjecture. We'll find it to be a property, so true, that is, about how these things are related. So let's compute the surface area and volume of a cube of side length 1. Okay, so if we have a cube of side length 1, okay, the surface area would be 1 square unit for each face, and there are 6 faces. So the surface area would be equal to 6. And then the volume, of course, length times width times height, length times width times height, however you want to say that. Anyway, it would be 1 times 1 times 1, so 1. Now let's do the same thing where the dimensions of the cube are 2, so all the side lengths are 2. So now each face, each side, has a surface area of 4. 4 times the 6 faces, so the surface area would actually be equal to 24 in this case, right? 4 times 6 is 24. And then the volume would be equal to, so I suppose just a V there, volume would be equal to 2 times 2 is 4 times 2 is 8. All right. So if SF is the scale factor, as we've been working with, AF is the area factor, and VF is the volume factor for a pair of similar solids, then how do you suppose they are related? Well, we already know that the area factor is equal to the scale factor squared. So here where we doubled, right, the scale factor was 2. Okay, we multiplied the area by 4, because 2 squared is 4, and then we multiplied the volume by 8, which would be 2 cubed. So, as you might suspect, the volume factor is equal to the scale factor cubed. So we can use that to help us answer some questions about surface areas, side lengths, and volumes of objects. All right, so we've got 4 examples here that we want to take a look at. So suppose we have a regular hexagonal pyramid. So 6 sides, 1, 2, 3, 4, 5, 6, and it's a pyramid. So we've got something that looks like this, of course. And it has a side length of 5 feet on the base, so side length of 5 feet, and a volume of 65 cubic feet. So if we have a similar pyramid that is, it's the same shape, but it's a different size, right? So if a similar pyramid has a side length of 8 on the base, what is its volume? Well, we would need to determine the scale factor first, and then we could determine the volume factor, and from that we can take the volume of the smaller pyramid, which we know, and find the volume of the larger pyramid. So for the scale factor, if we want to take the 5 and turn it into an 8, then the scale factor would have to be, so we need to multiply by something that's going to take 5 and turn it into 8, right? So we divide by 5, multiply by 8, and then simplify this fraction. Well, it's already simplified, so this is the scale factor. Then the volume factor is equal to the scale factor cubed. All right, well, 8 cubed I don't know off the top of my head, but fortunately I calculated that ahead of time. So that's 512 divided by 5 cubed, which would be 125. Excellent. So then the volume that we're interested in finding is 65 times the volume factor of 512 divided by 125, which is equal to, it simplifies a little bit, so if you want to punch it into your calculator right from here, that's fine, but you could also find the simplified fraction of 6,656 divided by 25. And then you say to yourself, well, I still want to put it in my calculator, that's fine. So 266.24 cubic feet. Excellent. So that is the volume of the larger pyramid. All right. So next we have a right triangular prism has a volume of 25 cubic meters. What is the volume of a similar prism whose base has twice the area as the first? So what we're saying there is that we have a area factor, right? It has twice the area, so we're saying the area factor is 2 here. That tells us the scale factor is equal to the square root of 2, right? Because the area factor is the scale factor squared. Square root 2 squared gives us the 2. And the volume factor would be equal to the square root of 2 cubed, or 2 times the square root of 2. So we can calculate the volume to be 25 times the volume factor of 2 times the square root of 2, which is 70.71. And that's, of course, cubic meters. Yes, excellent. So an 18-inch statue of a war general is made of solid bronze and weighs 45 pounds. The sculptor wants to make a 9-foot-tall version of the same statue, also out of solid bronze. How much will the large statue weigh? So we don't have a weight factor, but we can think of pounds, right? Bronze has a particular density, which is pounds per cubic foot. So we would have, or pounds per cubic inch, however you want to think of it. So this is associated to the volume. So we can multiply this by the volume factor to get ourselves the weight of the solid bronze. Okay. Let's see here. Okay, so we have to find the linear factor, or the scale factor. So we have an 18-inch, so the scale factor. We want to take an 18-inch or a 1.5 foot statue and bring it to a 9-foot statue. So we want to get rid of the 1.5 and multiply by 9. So that takes our 18-inch and makes it 9 feet. So we can actually write that a little bit differently. 9 divided by 3/2 would be 9 times 2/3. So that would be a scale factor of 6. Excellent. So that gives us a volume factor of 6 cubed, or 216. So then the weight would be equal to 45 times 216, right? Weight times the volume factor and this would be equal to 9,720 pounds. Heavy. That 9-foot statue would be heavy. All right, and then here's an interesting question. By what percent should you increase the side lengths of a cube in order to double the volume? So we want the volume factor to be equal to 2. That tells us that the scale factor should be equal to the cube root of 2, which is about 1.26. So we would have to increase the side lengths by 26% because this is 126% of what it used to be. So it's increased by 26%. So increase by 26%. Excellent. And that's all that we're looking for there. Now, for those of you that are interested, in fact, I would encourage all of you to watch the next video. Well, it might not be the next video, but watch the video on the calculus-based proof that the volume of a pyramid is in fact given by 1/3 times the area of the base times the height. And I'm not going to do that right now, just because I think it's a little bit more beneficial to spend more time on this. So it's a new idea, so we'll just do another video for it. But please watch that video for the volume of a pyramid given by this, and that will be posted a little bit later. Thank you guys for your attention today and your time. I hope you guys are having a great day, and I will see you again soon.